Hi, everybody. This is Mr. Folly, and I am doing this in a crowded lunchroom while you guys are having fun at the field trip, I hope. So, hopefully, I can hammer this thing out pretty quick. KMT is the kinetic molecular theory, and we're going to learn all about that. STP is standard temperature. Oh, my goodness, I know that. That's 0 degrees Celsius, which is 273 Kelvin. This is the number we'll use. And pressure. And that pressure is going to be 1 atmosphere, which equals 101.3 kilopascals, which equals 760 millimeters of Hg, which equals 760 torr. So those are the units, those are our reference points to do it. So let's go ahead and check the next one. Pressure. So let's talk about pressure. We do a neat little activity when we get into class. Pressure is only important for gases. Pressure is the force of a gas on the container. So this thing cruising around here doesn't really have a force, but when it hits the wall, boom, we have force. Okay? So we have pressure. So pressure is force over area. So let's talk about it. Barometers measure pressure. This is really a manometer. So you don't have to draw this or anything. But a barometer is the instrument that measures pressure. And pressure is in atmospheres. And again, 1 atmosphere equals 760 millimeters of mercury. We're going to have to convert from this. Equals 101.3 kilopascals. And remember, a millimeter of mercury is the same thing as a torr. The description of why gases behave as they do is called the kinetic molecular theory, often called KMT, which is what I'm going to call it. The first part is gas particles are point masses. That means if I have a box and I have steam in there, see how I drew steam? And it's like, oh, look, that's kind of like an inch by an inch by an inch. Nope. The particles are so small, they're like a dot. Wait. They're a point. Remember, points have no volume. Okay. Particles are not attracted to themselves or the container. This seems weird. No gravity, no intermolecular forces or anything. Particles move in rapid, random, straight line motion. This makes sense to me. Right? And collisions are perfectly elastic. That means they lose no energy and they don't slow down. Okay? So, here's the bad news. Kinetic molecular theory does a lot of rounding. The particles have volume, but it's negligible. So, their volume isn't 0, but it's almost 0. So, we're going to treat it like it's 0. Particles have attraction, but it's small. It's so small, it doesn't matter. It's kind of like the heartbeat that you have where it's like, oh, I don't want to step on that ant or smash that ant that's crawling up my leg. You don't think about it for very long, okay? Particles do lose energy in collisions, but it's very, 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 very small. And the only thing that is perfect is they do move in rapid random motion. All right. If you follow the kinetic molecular theory perfectly, you are ideal like a Disney princess. So what this means is we're going to maximize the truth of KMT. How do we do that? So we want these things to be most ideal. So if they're hot, right? Hot means the particles move faster. So when we talk about bouncing, so if particles are moving fast, there's less time for attraction because you're zooming right by, right? Who would you be attracted to? Someone who zooms by you in the hallway or someone you sit next to and talk to for a while, right? Hot also reduces elasticity as better. If you want to bounce a ball and have it bounce back up to you, the harder you throw it, the more perfect the bounce. Okay? So I know it's creepy to say that, excuse me, that Disney princesses are hot, but it's odd enough to make us remember. They have no friends. They're unattractive. Who are Belle's friends? She doesn't have any. Who are Sleeping Beauty's friends? She doesn't have any. Who are Snow White's friends? She doesn't have any. Who are Cinderella's friends? She doesn't have any. Remember, they're really dishes and candlesticks and mice. Okay. So we're going to point, that's the no friends. They're unattractive. Okay. So what that means in chemistry is you prefer to have dispersion over the other ones. Low pressure, so when I just read the pressure is that. Live in a big castle, what that means in chemistry is a big volume. Now what I mean by low pressure is you never heard Snow White saying, oh, oh, Prince Charming, or whatever your name is, we have to get married and move our lives forward together. No, that doesn't happen. That's low pressure, right? High pressure would be demanding that. Living in a big castle, they all live in a castle, so that means that if I'm in a big castle and I'm this little dot, my size matters less than if I'm in here. I'm the same size dot. See how this might be 1% of it, and this might be 6% of it, right? So I just get an idea. And then this is just a joke. So Boyle's law, it relates volume to pressure. As volume goes down, pressure goes up. Okay. As volume goes up, pressure goes down, and that is written as P1V1 equals P2V2. And you do need to know this is the graph. So if this is an inverse relationship, inverse means you get this graph. Inverse does not equal this. It's curved. Okay? Charles's law. Oh, Boyle's law. So I remember Boyle's law, and you don't need to know the names. You're good. Charles's law. Temperature and volume. So V1 over T1 equals V2 over T2. Notice how it's a straight plot. That means it is directly proportional. The hotter the particles move, the hotter particles move faster, so the volume increases. Hot particles move faster. Okay. And on this, we're going to do this in class in the next day or so. When you spray out cans, the hottest particles are going to leave out of the can. So what happens is the can gets colder. And we'll see that in the demo we do tomorrow. Gay-Lussac's law, temperature and pressure. P1 over T1 equals P2 over T2. As temperature goes up, it hits the sides harder, increasing it. As temperature goes down, pressure goes down. Graph, boom, it is directly related. So everything's directly proportional except for Boyle's law, which is PV equals PV. Combined gas law. P1 V1 over T1 equals P2 V2 over T2. So can you tell, now we're not doing a lot of these problems right here, but can you tell this is the math world of it? So all we're going to do is substitute and solve. Got one more. We've got Dalton's law of partial pressure. This isn't the evolution guy. It's a different guy named Dalton. And what he said is if you've got a mixture of gases, so do you see how I've got some hydrogen mixed in with helium? And if hydrogen's pressure is 0.6 and helium's pressure is 1.5, then the total pressure is adding them all up. So what that looks like is pressure 1 plus pressure 2 plus pressure 3 ... equals pressure total. So you just got to add them all up. This is super simple, right? So if I have my law of adding drinks up, here's my coffee. If I add 20 milliliters, and I add another 20 milliliters, and I add 10 milliliters, then I have 50 milliliters. Add them up. Woo! So where do we use Dalton's law? So we like gases because they do cool things. When you collect a gas, you're doing something here that generates a gas, and it's going to bubble into water. So this starts off being all the way full, and as it bubbles, it pushes the water out. And then when I'm done in here, what I want, so let's say the gas I'm generating is hydrogen. So I want this to be all hydrogen, but sadly, it is not all hydrogen. Anytime you collect it over water, and honestly we have to, you also get some H2O, which is what I put H2O there for. Okay, so we have to subtract the pressure of water because water evaporates a little bit. Ideal gas law. So this one's crazy. So this includes moles. Our first touch of moles. A mole will count the number of particles. I want to say atoms here, but they don't have to be atoms. They can be compounds. Okay? So PV equals mass RT over molar mass. Pressure, volume equals mass RT. R is a constant. It's kind of like pi. It'll be given to you right on the board. We're going to use 0.0821 liters atmospheres per mole Kelvin. Okay? And our pressure is going to be in atmospheres. Our volume is going to be in liters. That's going to be either moles or, see this N is moles, or we can use mass and molar mass. And molar masses go to the periodic table, and masses in grams. Review. Here are the equations, and gases are treated as unattractive points that move around and bounce perfectly. Let's hit the next one. 15.2. Ideal versus real gas, which we talked about a little bit. Okay? Pressure flow, effusion, diffusion, collecting gas over water, and molar mass of the gas, and density of the gas at STP. So here we go. As much as gases were ideal, they're actually real. Oh, look. We talked about how Disney princesses have some ideal characteristics. And oh, there's the Mrs. Folly. Isn't she adorable? Pressure flows from high to low. So if we have an airplane right here, if the pressure inside the airplane is high and the air in the sky, then on TV shows, when they shoot a bullet and it busts out, because the pressure inside the cabin is high, it's pressurized. Then as soon as the slightest hole, everything gets sucked out of there. All the air goes, and the oxygen mass falls in. Okay? So if there's a hole in Mr. Peanut here, Mr. Peanut might have a pressure of 1.75 atmospheres when he's blown up. Guess what? The atmosphere is 1 atmosphere. So what happens? The air will keep going out until it's just like Honda balloon right here, and it's going to be 1 atmosphere in and 1 atmosphere out. Okay? So what do you need to know? Pressure flows from high to low. Effusion versus diffusion. Stink diffuses. Pinholes cause effusion. Stink diffusion. Diffusion just means it spreads out. Effusion is spreading out after going through a door. Whoops. And it's usually a pinhole. Oh, I don't know why I'm getting these crazy lines, but I am. Right? The equation is crazy. Rate 1 over rate 2 equals the square root of molar mass 2, let's go to the periodic table, molar mass 1. Okay? So that's the speed of them. So I need to have 2 gases to compare them to each other. All right? CH4 diffuses at a rate of 0.137. How fast would oxygen's O2 diffuse? So remember, rate 1 over rate 2 equals square root molar mass 2, it's inverted, over molar mass 1. So rate 1 is CH4, 0.137. How fast? That's what we're solving for. Molar mass 2 is oxygen. Periodic table says 32. 16.01 for this. Do the math. Okay, does that make sense? And this one, just so we know it, helium, which weighs 2, and this weighs 16.04, lighter, moves faster. Why can Aiden run so much faster than me? I'm carrying around a little extra, aren't I? Let's be honest. I'm sitting outside of a Stan's Donuts. Density of a gas at STP. All right. Density is constant. Density equals love. Density equals mass over volume. See how it's a heart? It's a heart with a knife through it. All right. So what we have is we're going to assume 1 mole. What is the mass of 1 mole? Mass is go to periodic table. What is the volume of 1 mole? Hey, volume of 1 mole always equals 22.4 liters. Isn't that nifty? So, find the density of fluorine gas. That's F2. Density equals mass, 38 from the periodic table, over 22.4. Get an answer? Argon gas. Density equals mass, 18.02, I think is argon. I don't have the periodic table with me, over 22.4. Get your calculators out and do that. All right. Our first lab, we're actually not doing that lab, so goodbye. Here's the second lab. We're doing this one. We're going to react a metal with acid to create hydrogen. So we have this device right here. We've got a piece of magnesium. This is acid, right? And water, and it's going to mix. And when it mixes, it's going to start making gas, which is going to push it down. Okay? We're going to collect the gas over water and do PV equals nRT. All right? So when we do this, we're going to have, I'm going to blow this up quite a little bit here. Here's my beaker. We have to make sure that this line right here has to equal the other one. Okay? So if this line is the same, that means the pressure in equals the pressure of the room. Check. The temperature equals the temperature of the water. Little thermometer. Check. The volume, we can read the volume right here. Right here's my volume reading. Check. I've got pressure. I've got temperature. And then I can solve for R, or I can solve for N. Remember, N is mass over molar mass. So if we want to find out how much hydrogen we get, we won't be able to find the mass. So that means that means we're going to find, we're going to use R, which is 0.0820 0.06 liter atmospheres over mole. Don't worry about the units. They all cancel out. Review. Oops. We pretend all gases are real. No, we pretend all gases are not real, are ideal. Gas flows from high to low. Effusion is diffusion through a hole. Density is love of a mole. 22.4 liters equals 1 mole. Oops. That's it. Toodles.